Hello, grade 12s. Today's lesson is on the common ion effect. So we're still going to be looking at situations of Ksp equilibria, but what happens when we apply Le Chatelier's principle? What happens when we add a common ion or a stress? Well, according to Le Chatelier, when we apply a stress to a system, the system moves to reduce the effect of that stress. Suppose I have a solution that's got silver chloride dissolved. When silver chloride dissolves, it breaks apart to form silver +1 ions and chloride -1 ions. And very little silver chloride will actually dissolve in the water when it hits equilibrium. The Ksp for silver chloride is 1.8 times 10 to the -10. That means if I multiply the concentration of silver ions times the concentration of chloride ions together, I get this very, very small number. Now, back in grade 11, we taught you that silver chloride was effectively insoluble. Again, it's not that it's insoluble exactly. It's just that very, very little amount actually will dissolve. So what do you think would happen to this situation if I were to go and add silver nitrate to the solution? So here's a container of silver chloride. We can see that we've got silver ions in solution. They're all dissolved into the water, and chloride ions in solution. This solution is now saturated. If it's at equilibrium, it means it's holding as many silvers and as many chlorides as it can. If I add silver nitrate into this container, you'll notice that there's an ion in common. Both have silvers, but this solution that we're considering has chloride and this one has nitrate. So when I add silver nitrate to the solution, I'm adding more silver ions, and I'm also adding nitrate ions. Now, the nitrate ions have nothing to do with the silver chloride scenario, so we're not going to consider them at the moment. But look what I've effectively done. There's now more silver in this situation than there was before. You can see we've effectively increased the amount of silver. Now, if I increase the amount of silver, the equilibrium will want to decrease it. And the only way it can do that is to take some of this excess silver ion that we have here and react it with the chloride ion, together making silver chloride. Now, the silver chloride is a solid and will fall down to the bottom of our container that was already saturated. That has effectively gotten rid of the excess silver. It's also reduced the amount of chloride ions in the solution, and less of the silver chloride was dissolved. In other words, the salt becomes less soluble than it was before. The Ksp cannot change because we've changed the concentrations. It will shift in the direction to undo the stress. So we see that the silver nitrate ionizes to both form silver ions and nitrate ions. The extra silver ions, the ion in common with silver chloride, will combine with the chlorines in the silver chloride equilibria and precipitate out a solid silver chloride until the Ksp is once again equal to 1.8 times 10 to the -10. So the solubility, the amount of silver chloride, has effectively been lowered by the addition of a common ion. This is what we call the common ion effect. So how do problems look like when we have common ion effect? How do I know if a problem is just a regular Ksp problem or if it's a common ion problem? Well, here's some clues that you can use. First of all, we're going to see in the problem two different salts, and they're going to have an ion in common. In the example at the bottom, you can see we have iron hydroxide, one salt, and sodium hydroxide, a second salt. Both of them have an ion in common, that ion being the hydroxide ion. Now, when we compare the two salts, one of those salts is usually very soluble. In this case, sodium hydroxide, because it contains a group 1 ion, is a highly soluble salt. The other one is typically insoluble. We know iron hydroxide is an insoluble salt, and if you take a look on your periodic tables on the cheat sheet side, you'll see that I've given you the same set of 5 solubility rules that we go over in grade 11. So solubility rule 1 says any salt with a group 1 ion is always very soluble, so my sodium hydroxide is soluble. And solubility rule 5 says that Most salts that contain hydroxides, amongst other things, are insoluble unless attached to a group 1 ion or ammonium. And this is not an unless, so of the two, iron hydroxide is my insoluble salt. So this problem here has all the criteria for me to know it's a common ion question. But let's see if we can figure out how we'd solve it. When I have a common ion question, I see that there's two different salts, iron hydroxide and sodium hydroxide. One of these salts is going to get the big. What are the big three steps again? Well, step 1, of course, will be to write a balanced equation. Step 2 is to write the molar ratio. And step 3 is to write the Ksp expression. But which of these two salts get those big three? In this case, it's going to be the iron hydroxide. There's a couple of ways you can tell. The insoluble salt, the one that has the lower solubility, is typically the one that will go to equilibrium first. So, of course, that would be the one who gets the big 3 steps. Another way to tell is, did they give you the Ksp or ask you for the Ksp for one of the two salts? If they do, that's another indicator that that is the salt that's going to get the big 3 steps. Okay, so now that we've decided that iron hydroxide is going to get the big 3 steps, let's break this down. Step 1 is your balanced equation. When iron 3 hydroxide breaks down, it breaks down to give you 1 iron with a +3 charge and 3 hydroxides with a -1 charge. Since iron hydroxide is an insoluble salt, we're going to use two-way arrows. We know that this situation is going to go to equilibrium very quickly, and we know that we need an equilibrium reaction to be able to write our Ksp expression. Step 2 in our big 3 steps is to do the molar ratio. I want us to leave a little bit of space here because rather than doing just a simple molar ratio, we're actually going to do something called an ice chart. So underneath our balanced equations, where we normally put a molar ratio, we're going to write the letters I, C, E. I stands for initial. What is the starting amounts that we have? C stands for change. How do those initial amounts change as a result of establishing equilibrium or as a result of adding another salt with an ion in common? And E stands for what is the effect of that change. Some people like E to stand for where are the values at equilibrium. Either way, an ice chart allows us to figure out what's happening in the equilibrium before we try to put those values into a Ksp expression. So let's take a look at what values we could put in place of initial, change, and effect. Well, initially, when I put iron hydroxide into a solution of water, some amount X will go into the water, and none of it will have yet had a chance to break down to form iron and hydroxide ions. Of course, over time, some amount X of the iron hydroxide will break down and be dissolved. An X here, it refers to the solubility of iron hydroxide. The amount of iron that we have from the balanced equation will be the same amount that will go into solution, and the amount of hydroxide that we get from the iron hydroxide that breaks down will be 3 times this. So we have a value of X to X to 3X. But there's more stuff going on than just iron hydroxide breaking down. We also have to deal with the sodium hydroxide. So off into the side and into the same pot, we're going to consider what's happening with sodium hydroxide when it goes into water. Sodium hydroxide is considered a very soluble salt. When salts are very soluble, we use a one-way arrow. That means all of it will break down. We've put 0.05 moles per liter of sodium hydroxide into this container. Since we know that all of it is going to break down, we can see that we will get 0.05 moles per liter of sodium ions and also 0.05 moles per liter of hydroxide ions. So hydroxide is the ion in common. Both salts have hydroxide. So in addition to the 3x amount of hydroxide that we're getting from the breakdown of iron hydroxide, we will also be adding 0.05 moles per liter from the sodium hydroxide. So in addition to the 3x amount that we have from here, we will also add another 0.05 moles per liter from the addition of the sodium hydroxide. So what's the effect of this? What values do we have when we reach equilibrium? Well, the amount of iron is remaining unchanged, so the effect is we're going to leave iron at a value of X. We still don't know exactly how much we're going to get. The amount of hydroxide we're going to have will be 3x amount from the iron hydroxide plus another 0.05 amount from the sodium hydroxide. Now this total value is still going to be about 0.05. Remember, the amount of hydroxide I got from the iron hydroxide will be very, very small. Had I just multiplied these two values, x and 3x together in the Ksp expression, I get this value of 2.8 times 10 to the minus 39. So the value for x is going to be in the order of the minus teens. This only has a decimal point to minus 2. Even if I were to use the quadratic equation and say that this value is now 0.05 plus 3x and use the quadratic equation in the Ksp expression to solve for x, we would find that after I adjusted for significant digits, it would still work out to being about 0.05. So where my amount here is so small compared to the amount that we're adding from the salt in common, we can say effectively that the concentration of hydroxide will now be about 0.05. Okay, now we're going to get to the big three of my big three steps. We have the balanced equation, and we've done an ice chart in place of a molar ratio to get the values for iron and for hydroxide. I'm not worried about figuring out the effective amount of iron hydroxide at equilibrium because it's a solid and is not a part of my Ksp calculation. From a balanced equation, I can see that my Ksp will be equal to the concentration of my iron 3 plus ions times the concentration of my hydroxide 1 minus ions cubed. Remember, the balancing in the balanced equations becomes the exponents in the Ksp expression. Okay, now that I have my Ksp expression, let's substitute the values inside the brackets. We know the concentration of iron at equilibrium will be X. We know the concentration of hydroxide at equilibrium, in this case, is going to be about 0.05. And I know the Ksp for iron hydroxide is 2.8 times 10 to the minus 39. So we'll just substitute those numbers in place for each of the variables in the equation. Ksp is given as 2.8 times 10 to the minus 39. Concentration of iron we know to be X. Concentration of hydroxide is about 0.05 cubed. Now again, had you left this as 0.05 plus 3x, you'd now be using the quadratic equation to solve for this value. We're going to find out that the value we solve to find for x will be about the same regardless of whether or not you do that step. At the grade 12 level, I'm not worried about you guys using a quadratic equation to solve for a problem. Substitute the values. Know that the overall amount of hydroxide will be about the same as what's provided by the common ion, and let's go from there. Okay, so our order of operation is to cube the 0.05 first. Always take care of your exponents first. That will give us a value of 1.25 times 10 to the minus 4. And then to get x by itself, we'll take that value over here and divide. So 2.8 times 10 to the minus 39 divided by the cube of 0.05, or 1.25 times 10 to the minus 4, will give us our value for x. And then we solve for x and get a value of 2.24 times 10 to the minus 35. You can see that had I taken 3 times this amount and added it to the 0.05, you still would have had 0.05, 0.00000 30 some times to 24. It would have rounded back out to 0.05. The value for x is very, very small. Now, again, just because we've done the math and solved for x doesn't mean we've actually answered the question. At the point of solving for x, I always need you guys to go back and say, what was it they asked me to find anyway? Now, referring back to the question, it had asked us, what is the molar solubility of iron hydroxide? Up above in our ice chart, we had defined the molar solubility, the amount that dissolved, as being x. Remember, an x on the left-hand side of the arrow talks about the molar solubility, how much dissolves. These values of x, x and 3x, tell you the concentrations of the ions at equilibrium. So now that we have actually done the math, we should answer the question. This can be done as simply as saying this value for x is the molar solubility of iron hydroxide. Okay, there's going to be some time that you're going to need to practice a whole lot of problems like this. I'd like you to start by opening up your workbook section of your package to about page 4 and 5. The title there is Ksp and Common Ion Effect. On those 2 pages, you'll see questions from 1 up to 14. And I'm going to give you guys a couple of days to practice those. If you get stuck on any of them, drop me a message and I will work through them for you. Always start with deciding which of your 2 salts is your big 3. The one that is insoluble, who gets the big 3 steps. And remember that the other salt will be the one that provides the common ion. Once we've got that figured out, we are at a Ksp expression again, and either the question is giving us the Ksp and asking us to find one of the unknowns, or it's giving us the values on this side and asking us to find the Ksp. Again, there's really only 2 ways to go with that. So again, you guys can work on pages 4 and 5 in the workbook, Ksp and Common Ion, questions 1 through 14.